Hey guys, what's up? Welcome back to our review session. We are just about done. This is going to be just like a handful of problems I randomly picked from the book, and we're going to throw them at you and see what we can do with them. What I'm going to do probably is work through these, at least as many of them as I can, and try to show you tables along the way and steps that I take. But yeah, let's see what happens. It's just a bunch of hypothesis testing, basically, confidence intervals, stuff like that. I didn't hit everything, but I just pulled out some random stuff all the way through ANOVA. I didn't put any linear regression stuff on there because we just covered that, and I kind of ran out of time when I was typing these up. So just go for it, see what happens. Review the linear regression stuff, all the chapter 12 examples that we did. So this is by no means like an exhaustive list, but it's just a few review problems. So just take it at that. Don't necessarily think this is going to be just like the exam. This is just a bunch of problems. So throwing that out there. I just typed these up straight from the book. Yeah, it's not really an exam. I forgot to take those off when I was making this review sheet today. So anyway, not really an exam. Let's see. The first one says the melting point of each of 16 samples of a certain brand of hydrogenated vegetable oil was determined, and the result was that X bar was 94.32. Assume that the distribution of the melting point is normal with a standard deviation 1.20. Test H0, the null hypothesis mu equals 95 versus the alternative mu is not equal to 95 using a significance level of 0.01. So this one should be pretty straightforward, I hope, like see what we can do. Number one here, we're going to calculate Z equals X bar minus mu over sigma over square root of n, which is going to be 94.32 over 1.20 over square root of 16. And crunch that in our calculator. 94.32 divided by 1.2, basically times 4. Whoops. 94.32 minus 95. There we go. Try that again. 94.32 minus 95 divided by 1.2 times 4. It's negative 2.266 repeating. And I'll probably just round that to 2 decimal places so I can use my chart. On the exam, I think I'd tell you to do that too. So we'll use absolute value of Z to be 2.27. So what is the P value? So P is going to be 2 times 1 minus phi of 2.27. So I looked that up in our chart. Pull up the Z table. There it is. And so I'm looking for phi of 2.27. Let's see. So we're looking for phi of 2.27. Let's see, 2.2 is this row. And let's see, did I round it? 2.27. So 2.2 and then column 7 here. So 0.9884. So 2 times 1 minus 0.9884. So 1 minus 0.99884 times 2. So P is 0.23202. Sorry. 0.0232. Now, we're testing with alpha is 0.01, so no. Fail to reject H0. Fail to reject H0. So even though our sample was 94.32, this is not strong evidence to reject the null. No, yeah, it's literally just problems I typed up from the book. Like this is, it says all this stuff in here because I just copied the format and kind of replaced all the exams, changed a few things. I forgot to change this title here. Like I copied an old format, and it's not the exam from 2017. It's a different from 2017. I could show you it's different. I literally typed all these up today. Okay, so the test Monday will be chapters 8, 9, 10, and 12. The test Friday this week, 2 days from today, will be chapters 1 through 7. Okay, so why am I taking absolute value here? Because I'm doing this 2 times business. And my alternative is right here. So when I have the alternative hypothesis mu is not equal to a value, or any case, basically anything not equal to a value, we do 2 times what's to the right of the positive, or the absolute value of the test statistic. It's all based on your alternative for how you get that p-value. So this right here is telling me to do the p-value equals 2 times 1 minus phi of absolute value. So hopefully that kind of clears everything up for Justin and Eric. That's why we're doing 2 times. All right, number 2, similar. Number 2 says the desired percentage of silicon oxide 2, I guess you would say, SiO2, in a certain type of aluminous cement is 5.5. So 5.5% of that cement is SiO2. To test whether the true average percentage is 5.5 for a particular production facility, 16 independently obtained samples are analyzed. Suppose that the percentage of SiO2 in the sample is normally distributed with average or standard deviation 0.3, and that X bar from that sample was 5.25. Based on those numbers, is there strong evidence to suggest that the average is not 5.5? Explain what you consider to be strong evidence. All right, so got H0. We'll do a hypothesis test here. Mu equals 5.5. The alternative, let's see, based on their wording, is there strong evidence to that the average is not 5.5? So we'll say mu is not 5.5, meaning we'll multiply by 2. And X bar is 5.25. sigma is known. Yeah, 0.3. And see, that's n equals 16. So part A here, if I calculate a test statistic z in this case, because it's normal and I know sigma, I calculate a test statistic x bar minus 5.5 over 0.3 over square root of 16. That gives me, let's see, 5.25 minus 5.5 divided by, so that's negative 0.25 divided by 0.3 times 4 is negative 3.33 repeating. And because I'm doing 2 times again, right, I have the alternative not equal to, my p-value is going to equal 2 times 1 minus phi of absolute value, negative 3.33. So that's going to be 2 times 1 minus, now I have to look up 3.33 in my chart. 3.33 is right here, 0.9999996. So 1 minus 0.9996. 1 minus 0.9996 times 2 is p equals 8 times 10 to the negative 4, or we could say 0.0008. Yeah, we're definitely rejecting the idea that mu is 5.5. So definitely reject H0. I would say anything less than like 1% is pretty low. You do not take the absolute value in the less than or greater than alternatives, only in the not equal to alternative. So just like Sam said there, it's only in the not equal to alternative. Just kind of highlight that in blue here. So, in my opinion, p less than 0.01 is strong evidence. I'll skip part B. And move on to number 3. For question 2, what is P being compared to? Yeah, so in question 2, it's actually kind of, we just have to go off of our gut. And this P value is really, really small, like 0.0008. That's really small. So we could kind of say, okay, that's strong evidence in our opinion, kind of. So we didn't like explicitly have something to compare to. This is more of like your reasoning based on the results, if that makes sense. That's a great question. All right, so number 3, this says the following observations on stopping distance in feet of a particular truck at 20 miles per hour under specified experimental conditions. The cited report states that under these conditions, the maximum allowable stopping distance is 30 feet. A normal probability plot indicates that stopping distance is normally distributed. Does the data given suggest that under these conditions, the true stopping distance exceeds this maximum value? Test the appropriate hypothesis using alpha equals 0.01. Well, basically, we have to calculate x bar and s ourselves. So x bar equals what? S equals what? So I need to calculate the average and the sample standard deviation. So I'm going to add these values together, 32.1 plus 30.6 plus 31.4 plus 30.4 plus 31 plus 31.9 divided by, see, I think that's 6 observations, 1, 2, 3, 4, 5, 6. So divided by 6, I get x bar equals 31.23 3 repeating, and I'll store that in a variable. I'll call it a, and then I'll do 32.1 minus a quantity squared plus 30.6 minus a quantity squared plus 31.4 minus a quantity squared plus 30.4 minus a quantity squared plus, so now I'm calculating s squared basically. Let's see, plus 31 minus a quantity squared plus 31.9 minus a quantity squared. I get 2.373 repeating, so it's going to be 2.3733 repeating over n minus 1, in this case 6 minus 1, so divided by 5, and then s, take the square root of that, so square root of that number, I get s equals 0.68896. So 0.68896, and that is rounded, but the next digit was 0, so it's pretty close. So I've got my sample standard deviation from our calculation, and I've got the average, so now we can get our t statistic. So our test statistic t in this case. So t is going to equal x bar minus 30 over s over square root of 6. And that's going to be 1.233 repeating over s over square root of 6. So now I just plug and chug that. So a minus 30 divided by 0.68896 times square root of 6. And I get a t of 4.38492. And my degrees of freedom are 6 minus 1, which is 5. So now I gotta look at my p-value. What's the alternative here? So the alternative here, see, h0 is that mu equals 30. The alternative here is that mu is greater than 30. So this one, I just look at p equals t-curve tails. It's a probability that t is greater or equal to 4.38492, and degrees of freedom equals 5. So I gotta look up my t-curve tails chart. So t-CDF, and we're looking for the column 5, so right here, and we're going all the way down to 4.4, round it to 4.4. So 4.4 is on the next page. Oh snap, we should go down to 4. and column 5, which is this value here. So it's smaller than 0.005. So p-value is less than 0.005 for sure. Okay. So what can we say? Hard to say. Let's see. Sorry. Yeah, that's right. P is less than 0.005, which is less than alpha, which is 0.01. So we can reject H0 and say most likely mu is greater than 30. So yes, this data does suggest that the average stopping distance is larger than 30. I mean, every value there was larger than 30, so that kind of indicates it already. But to do a real strong significance, you know, a statistically significant test of whether or not it's, you know, valid, we have to go through this process. So it's like very unlikely that you would get this set of data if the true stopping distance were 30 feet. That's what this is saying. You would only get this set of data like less than 1% of the time. So like 0.5% of the time, you randomly select 6 vehicles to test, or trucks. Only 6%, sorry, only less than 0.5% of the time would you get this set of data. So it's very unlikely that you would get this set of data if mu were equal to 30. So yes, the data does suggest that under these conditions, the true stopping distance exceeds 30 feet. So that was good. That was a t-test because we had a small sample size and we had unknown sigma. So this was small sample, unknown sigma. To do a t-test. Let me see if I can do something really fast. Just trying to see if I could resize this text here. I'm just going to move it out of the way for now. Problem 1, 2. Three now. That's tricky. There we go, somewhere like that. All right, cool. Number 4. All right, so yeah, we use the t-test when n is small and we don't know sigma. So we use the t-test when n is small and we don't know sigma. On our exam, do we need to worry about a problem where the test statistic isn't on a chart? I'm going to try to make sure that they're calculate, like you can calculate them from the chart. Except for the ANOVA, right? The ANOVA, it's unlikely that it will be on the chart. It's going to be between 2 values or on the extreme or something like that. So on the ANOVA, probably not. So yeah. All right, let's go to number 4 here. So number 4, it says a manufacturer of nickel hydrogen batteries randomly selects 100 nickel plates for test cells, cycles them a specified number of times, and determines that 14 of the plates have blistered. Does this provide compelling evidence for concluding that more than 10% of all plates blister under such circumstances? State and test the appropriate hypothesis using a significance level of 0.05. So this is basically like testing P equals 0.15. So that's like our null. And our alternative is that P, 10%, so 0.10. Alternative is, let's see, based on the wording, more than, so greater than 0.10. So we've got P hat is 14 over 100, which is 0.14. So now we need to look at our test statistic for testing population proportion. And it's supposed to be a z-test. So z equals, let's see, p hat minus p over, if I'm not mistaken, I think it's p hat times q hat over the sample size. And this is where I'll get into trouble if I don't look it up. And so I'll just look it up real quick to make sure. This is where I can use my book, thankfully. And let's see, is this the right test statistic for Z? Or sorry, for hypothesis testing population proportions? Yes. Bam. That's it. So yeah, sweet. P hat minus P0. Oh, not over P hat. It's over P0. And P0, 1 minus P0 over N. Tricky. Yeah, that makes sense. You always want to use the proposed stuff. Okay. So that's going to be 0.14 minus 0.1 over square root of 0.1 times 0.9 over 100. We get our z value, our z score. Let's see what we get. 0.14 minus 0.1, we know what that is, divided by square root of 0.1 times 0.9 over 100. Close the square root. And I get this as 1.333. Repeating. Yeah, small we'll say is less than 40 if you don't know sigma. And if you know sigma, it's less than 30. But pretty much less than 40. Okay, wow, this is not a strong z value, is it? So let's look at the alternative. The p-value then is going to be 1 minus phi of 1.33. So 1 minus, when we look up our z table, 1.33, there it is, 0.9082. So 1 minus 0.9082. 1 minus 0.9082, and that's 0.0918. So 9% of the time this would happen if the true percentage were 10%. So what are we testing at? We're testing at a significance level of 0.05. So this is greater than alpha, which is 0.05. So fail to reject the null. Fail to reject H0. So this is not strong enough evidence based on this alpha. It doesn't matter because it's multiplication, so we can write it like this, or either way, it doesn't matter. So 0.1 times 0.9 over 100 is the same, either way. But it is under the radical, that's important. So this radical encompasses this whole, this whole thing. So that was part A, basically. And part B says, well, what if our null is now that p equals 0.15, and the alternative is that p is greater than, let's say less than 0.15. So that one's actually not super clear. I just made this one up more or less. So what if means test p less than 0.15, basically. So that should be more clear in the instructions, because it's not clear what you need to test because you're changing your null hypothesis. Okay, so now we've got a sample p hat, which is 0.14, and it turns out to be less than the true value, or supposedly the true value. We want to test if it's significantly less. So n now is 200. So our z statistic is going to be 0.14 minus 0.15 over square root 0.15 times 0.85 over 200. So let's see what happens now. So 0.14 minus 0.15 divided by square root of, and the open parentheses, 0.15 times 0.85 over 200, close the parentheses on the radical. Whoa, not even close. So it's going to be negative 0.396059. So p is just going to be phi of negative 0.3, or we'll just say negative 0.40. So it's definitely not even really going to be close. Right, our alternative here is p is less than some value, so I just use it directly. I don't do 1 minus. So let's see what this p-value is. So negative 0.40. It is right. Negative 0.40 is right here. Not even close. 34% of the time this is going to happen. So 0.34, 0.3446. So definitely not. So fail to reject H0. Good question. That's actually a great point. 14 of the plates are blistered. You're correct. Thanks, Bradford. Good question. Good call. Let's restart this one. Thank you. So now p hat is 14 over 200. Thank you. 14 over 200. Good call. So z now is going to be, let's see, what does that come up to be? 14 over 200. 0.07. So 0.07 minus 0.15 over square root 0.15 times 0.85 over 200. Aha, very good. Negative 3.17. We'll round it. So now, there we go. P is going to be phi of negative 3.17. And look that up in our chart. Negative 3.17 is here, 0.0008. Very good, Bradford. Thank you. 0.0008. Aha, yes, reject the null. There is strong evidence that P is less than 15%, so 0.15. Cool. Sweet. Okay. National Health Statistics reports dated October 22nd, 2008 include the following information on the heights for non-Hispanic white females. Aged 20 to 39, the sample size was 866 people, and the sample mean in inches was 64.9 inches. And so a little over 5 feet, so like 5 feet 4 inches, 4.9 inches. And then the standard error, we have to remember what that was, but that's actually the standard deviation divided by the square root of the sample size is 0.9. And then for older, 60 and older, sample size was 934 people. The sample mean was 63.1. The standard error was 0.11. Calculate and interpret a confidence interval at a confidence level of 95% for the difference between population mean height for the younger women compared to that for the older women. So we'll do younger minus older. So let's look at number 5 here. This is obviously a 2 sample stuff going on here in number 5. So number 5, we have 2 sample, large sample size. So that's important. We'll use a z statistic here. This is going to be a z-test because we have a large sample size. This is a z-test. And what did we need? Let's see, standard error. We'll even say that that's S over, so it's like S1 over square root of 866. And this right here is S2 over square root of 934. So that's what these two numbers are right here. So Z is supposed to be, oh snap, what are we doing? We're doing a confidence interval. So that's going to be x1 bar minus x2 bar plus or minus z sub alpha over 2 times, and then the standard error for the sample, the 2 samples, is s1 squared over m plus s2 squared over n. So that confidence interval, so you have alpha equals 0.05, so alpha over 2, it's going to be 0.025. And so z sub 0.025, I believe, is 1.96. Could look that up in our chart. And we could cheat. We could go to the t criticals and go down to the last row and look up 0.025, 1.96. There it is. So yeah, 1.96. A little cheat, you know, if you're looking up z critical and it's one of the special values, you don't have to use the z table. Special value meaning one of the top, you know, up here. Then you can just look it up in the t criticals in the last row. But we got it. So let's see, 64.9 minus 63.1 plus or minus 1.96 times square root of 0.9 squared plus 0.11 squared. So let's go ahead and calculate that number that we're adding and subtracting from 64.9 minus 63.1. So square root of 0.9 squared plus 0.11 squared times 1.96. And so we're adding and subtracting 1.77. So 64.9 minus 63.1 plus the answer. So the upper bound of the confidence interval is going to be 3.57713 if we round it. And the lower bound would be, let's see, so 1.8 minus 1.77. Lower bound is 0.02287, and we'll just round it there. So this would be our 95% confidence interval. And let's see, it says basically that the 20 to 39s, so mu 1 is at least greater than mu2 by 0.02287 inches, up to mu1 greater than mu2 by 3.577 inches. So we think basically that the difference is somewhere in here, meaning that the mu1, or the average of the younger women, is at least 0.02 inches more than the average of the older women. So we can say, yes, we are fairly certain that younger women are taller than older women. That's how we would kind of interpret this. So fairly certain, fairly sure, the 20 to 39-year-olds are taller than 60 and older year-olds. So that's kind of the part A of that problem. So the only thing that was tricky there was knowing what to do with the standard error. And the standard error is the standard deviation divided by the sample, or square root of the sample size. Well, in our test statistic, or sorry, it's our standard error for the sum, or the difference, we need to take the square root of the sum of the standard, I guess you could say standard variances, but it's S1 squared over M plus S2 squared over N, which we get by squaring the standard errors. So S1 over 2, or S1 over M square root of M is given as 0.9. So S1 squared over M would be 0.9 squared. So that's why we're doing that. So that's part A. We calculated and interpreted a confidence interval at confidence level 95% for the difference between population mean height for the younger women and that for the older women. That's right, 0.9 and 0.11 are already the standard errors, which is the standard deviation divided by square root of that sample size. Okay, let's see. Part B says let mu1 denote the population mean height for those 20 to 39 and mu2 denote the population mean height for those age 60 and older. Interpret the hypothesis H0 is mu1 minus mu2 equal to 1, and the alternative mu1 minus mu2 greater than 1, and then carry out a test of these hypotheses at a significance level of 0.01. So let's look at part B here. So it's basically part A that we calculated up here. And now part B says that H0 is mu1 minus mu2 equals 1. What does that say? That says we think that the average of 20 to 39 is 1 inch more than the average of 60 and older. That's basically what this null would say. Basically, you could say mu1 equals 1 plus mu2. 1 inch more than mu2. The alternative is that the mu1 is larger than 1 inch more. So the alternative HA is that mu1 minus mu2 is larger than 1 inch. So you could say the alternative here is that the 20 to 39-year-olds are more than 1 inch taller than the 60-year-olds and older. Now carry out a hypothesis test. Alpha equals 0.01. So our test statistic Z is going to be x1 bar minus x2 bar minus, in this case, 1 all over square root of s1 squared over m plus s2 squared over n. And so that is going to be, let's see, I think the difference is already 1.8, right? 64.9 minus 63.1 is 1.8. So 1.8 minus 1 over square root of 0.9 squared plus 0.11 squared. Get a Z statistic. Is this Z? We have a large sample? Yeah. Yeah, it's Z test, so Z stuff. So let's see. 1.8 minus 1 we know is 0.8 divided by the square root of 0.9 squared plus 0.11 squared. Ooh, not very good. It's 0.88. And we'll just round it. So that's our Z statistic. So p-value is going to be 1 minus phi of 0.88. So look it up on our chart. Go to the Z table and we go to 0.88. 0.88 is right here, so 0.8106. So 1 minus 0.8106. So 1 minus 0.8106 is 0.1894. 0.1894. So fail to reject H0. So there's not strong evidence to say that the difference is larger than 1 inch. Doesn't mean that the difference is 1 inch. It just means we didn't reject the idea that it's 1 inch, even though we got an average difference of 1.8. So the difference was 1.8 inches, but it wasn't statistically significant, especially with this super large sample size. That's crazy. Because those deviations were pretty large already. So yeah, that's two sample Z test. So you could have two sample T test. And you could also have two sample population proportions. We didn't go over that. I didn't put those on here, but those are still fair game. You know, that's like the rest of chapter 9 right there. So just a heads up. You know, that stuff that's also likely to be on there. The next one is paired data, and it's actually going to be t-test, so because it's small. Okay, number 6 here. I'll just get it started because I want to get to the ANOVA table. So let's maybe not go all the way through number 6. But I'll just get it started. Number 6 here. It says adding computerized medical images to a database promises to provide great resources for physicians. However, there are other methods of obtaining such information, so the issue of efficiency of access needs to be investigated. An article reported an experiment in which 13 computer proficient medical professionals were timed both while retrieving an image from a library of slides and while retrieving the same image from a computer database with a web front end. And here are the 13 results from the slides versus the digital access, and then the difference. Estimate the true difference between the average retrieval times for the two types of retrieval methods. Does the data indicate that they are different? Justify your answer by either hypothesis test at alpha equals 0.01 or a 99% confidence interval. I'll just go ahead with the hypothesis test. And so D bar, what's D bar? D bar is going to add up this last row right here to get D bar. So that's going to be 5 plus 19 plus 25 plus 10 plus 10 plus 10 plus 28 plus 46 plus 25 plus 38 plus 14 plus 23 plus 14. So 267 divided by 13, I get D bar is 20.53846. And I need the standard deviation, S. And so I'll store this into, we'll store it in D because it's D bar. So store that into D. And then I'll do 5 minus D quantity squared plus, so I've got to do the sum of X or DI minus D bar over N minus 1 to get the sample standard deviation. All right, so 5 minus D bar plus, or squared plus quantity, 19 minus D quantity squared plus 25 minus D quantity squared plus 3 times, I should do 3 times 10 minus D quantity squared. Just take advantage of the fact that there's 3 of those, plus 28 minus D quantity squared plus 46 minus D quantity squared plus 25 minus, minus D quantity squared plus 38 minus D quantity squared plus 14 minus D quantity squared plus 23 minus D quantity squared plus 14 minus D quantity squared. Okay, so that's going to be, I should take the square root. So square root of 1717.23 over 12. So I divide this by 12 and then take the square root. So I got S equals 11.9625. I'll store that into, I don't care, E, I guess. All right, so I got my D bar, and I got my sample standard deviation for D. Now, estimate the true difference between true average retrieval time. So I need to look this up just to make sure it's a t-test. I'm certain of that. I just want to make sure I do the right t-test. It's for paired data. So yeah, not bad. Yeah, pretty easy. So T is going to be, well, we got to give alternative and a null and all that stuff. So H0 here is going to be that the difference is 0, right? D equals 0. The alternative, we'll just go with the alternative D is not 0. Or we will say D is greater than 0. It does say they are different, so we'll say d not equal to 0. Now the test statistic t from the notes is that we do d bar minus 0, in this case, over square root, or sorry, s over square root of 13. So that's going to be 20.53846 over 11.9625 over square root of 13. I think it's going to be pretty large. And our degrees of freedom in this case are 12. So 20, well, actually what can I do? I can say d over e times square root 13. Oh yeah, it's really big, 6.19. So I'll just round it to 6.2 because my t-curve tails. So p-value now is going to be t-curve tails of 6.2, degrees of freedom 12. So t-curve tails, here it is, not even on the chart, degrees of freedom 12, so this column go all the way down, so it's less than 0.001. So p-value is less than 0.001. And that's less than 0.01, which is alpha, so reject H0. Yes. Oh, I need to multiply by 2, don't I? P is less than 2 times 0.0001, which is still less than 0.01. I need to multiply by 2 because my alternative here need to multiply by 2. So yes, significant that digital is less than slides. So there's a significant difference in these two. Statistically significant difference. And number 7 says, finish out this ANOVA table. Basically, an experiment was carried out to compare electrical resistivity for 6 different low permeability concrete bridge deck mixtures. There were 26 measurements on concrete cylinders for each mixture. So the number of populations is 6, and number of measurements is 26. So which one's I and which one's J? Well, I is the number of populations, so I equals 6, and J is 26. So now, what are our degrees of freedom? We can go ahead and get the degrees of freedom, right? So the treatments, degrees of freedom for the treatments is I minus 1, which is 6 minus 1, which is 5. And then for the error, it's I times J minus 1, so 6 times 25. Let's just say I minus 1, I times J minus 1. So put them in here, 5, and then 6 times 25 is 150, seems really large. Total is 155. And now what do I know? I know the sum of squares, I know the mean square error, MSE, is actually SSE over I times j minus 1. So I can actually solve for SSE by multiplying. So SSE equals MSE times 150. So 13.929 times 150 is 2089.35. And let's see, so now we've got SSE equals 2089.35. And so SSTR plus SSE equals SST, which I already know SST, so I can get SSTR as SST minus SSE. So 566.415 minus 2089.35. So 5664.415 minus 2089.35. And SSTR is 3575.065. 3575.065. And now I know MSTR is going to be SSTR over I minus 1. So that answer divided by 5 is 715.013. And now F is MSTR over MSE. So F is going to be MSTR over MSE, which is 715. So that answer divided by 13.929. I get a freaking huge F statistic, 51.33. So crazy big. All right, now the null H0 is that mu1 equals mu2 equals ... equals mu6. And the alternative is that at least one is not the same. So at least one is different. And let's see if I can find the F table somewhere. That's weird. I know I've got one somewhere. Just gotta find it. Let's see. Go to an old final somewhere. For sure I had, no, not there, because I printed them. It's got to be this one. Shoot. Maybe this one. Zipped up. Where did I put those? Let's see. Try one more place. I'll just look it up in my textbook here. So I'll look up the F distribution, my textbook. Okay, here we go. Let's see. Degrees of freedom number 1 is 5. Degrees of freedom number 2 is like freaking huge. So here we go. Ours is 150 for the second degrees of freedom. So, and we got a stupid large value. So either 100 or 200 on page A18. So page A18, V2 is 150. So on either one, with our F value, it's going to be less than 0.001. So our degrees of freedom were 5, so we'll go to this fifth column here. So if we're larger than 4.48 or 4.29, we're definitely less than 0.001. So our p-value is going to be less than 0.001, which is less than the alpha here. So it's pretty small. So probably reject H0. Our p-value is like super small, since our F statistic is much larger than 4.3. So F is much greater than 4.3. So our p-value is actually much smaller than 0.01. Yes, so test on Friday covers chapters 1 to 7. Test on Monday covers chapters 8, 9, 10, and 12. So we basically did 8, 9, and 10 today. I didn't go over anything from chapter 12, but that's all fair game. You know, all the hypothesis testing there, all the calculations, everything from chapter 12 is fair game too. So hang in there. It's almost over. The grading is going to be a little tricky. I'm going to, try my darndest to get the exam 1 or part 1 graded over the weekend by like Friday night or Saturday or something like that. So we'll see. And then you should be able to just hopefully focus on the second part. Well, I guess you should be focusing on that anyway. The rest is a review. So anyway, just kind of review everything and then really hammer all this chapter 8, 9, 10, 12 stuff. But yeah, that's what's up. Questions? If no questions, I'll see you guys Friday for the final exam part A. You guys are going to kill it. Pretty proud of you guys so far. This quarter, you've done awesome. Hang in there. It's going to be good. Summer's almost here. The test for Friday, I think it's going to be like 10 questions, about 10 points each. So, sorry, seven questions, about 10 points each. And it'll be 70 points total for the exam on Friday, and then 80 points total for the exam on Monday. So on Monday, there'll be more like 8 questions and 80 points. So about 10 points each. It won't be like huge hitters like 16 points like we had on some previous exams. So it'll be more like 7 questions on the first part, 10 points each, more or less. Maybe a 12-pointer, but yeah. Let's see. Yeah. Cool. Well, I'll see you guys on Friday. Have a good study session next 48 hours. And I'll see you guys then. Have a good one. Oh yeah, I'll post this whole review sheet thing on Moodle and the solutions that I've got here.